Okay, so how is the assignment going? I know some of you have questions and such, right? So I'm going to extend it till Monday, right? So assignment 4, due date. I'll just write it here and leave it here. Some of you wanted to meet and had questions, so I'll have time today and tomorrow, maybe during the weekend as well. So, okay, so that's that, and then we'll carry on from where we left in the last class. Before I proceed, any other things we need to discuss? All right. So if not, so what we have. 5 lectures left, including today, and here's the plan. We have talked quite a bit about electronic properties of semiconductors early on, band structure, a little bit of transport, quite a bit about photonic properties, optical transitions, absorption, emission, LEDs, and all. One of the things we have not talked about in terms of physical properties are thermal properties. And what I want to do is just this class today, I want to discuss about thermal properties of compound semiconductors. And then the last 4 classes starting next week will be all on growth and primarily epitaxy and things like science of growth of compound semiconductors, compound semiconductor heterostructures, MBE, CVD, and those things. Okay. So today's topic then will be thermal properties, in particular thermal conductivity of compound semiconductors, so we will dig in a little bit deep and go to the properties that actually the aspects of thermal conductivity that directly affect the operation and design of electronic devices, of photonic devices, and as is the case with pretty much all semiconductors, if you understand thermal conductivity, whether it's very high or very low, you can make use of it both ends of the spectrum. Okay, so as we understand. So thermal conductivity we will quantify very soon, but let me just start with the simplest picture of what we mean by thermal conductivity, and the analogy is really very similar to electrical conductivity. You have a block of material, and in electrical conductivity you're applying a voltage, right? Electrical voltage, potential difference between the two. And because of this potential difference, you have a current flow, right? And we write the a current as resistance, voltage over resistance, and have electrical resistivity, and electrical resistivity right as conductivity length over A. And I think we kind of know that this is under the diffusive regime. If you have ballistic transport, this doesn't quite apply, and such and such. So if you have scattering and all that, so here's electrical resistivity, and from here you get resistance is rho. No, what did I write here? Sorry, resistance is let me write it. That, right? Resistance is that, and resistivity. Electrical resistivity is 1 over electrical conductivity, right? So and that's what we connect to if you have electrons with a mobility of mu n, holes with mobility of mu p's, and so on. So that's your electrical conductivity, right? And one way to look at it is the electrical current density is electrical conductivity times the electric field, right? So that's the way to look at it. So in a very similar way, here, for example, your electric field, or when you multiply this expression basically by by the, let's look at linear dimensions 1D, right now. So that would become current. And from here, you can show that this will be basically V over R, right, where electric field over the length is equal to, let me write that down, right? And by changing the resistivity, etc., you can show that this basically V over R, right? And that's the standard Ohm's law picture. And we know, it's valid in a certain regime. If you apply very high voltage, high electric fields, current saturates, you deviate. If you have very small dimensions, transport occurs ballistically and not quite by diffusion, so you deviate and all that. So there are deviations, but this for dimensions which are a few microns and voltages that are not thousands of volts, this is a reasonable number, right? I mean, it's a reasonable model. In a very similar way, when you are instead of, if I apply electrical voltage across, if I apply a thermal gradient instead of a field voltage gradient, if I apply a thermal gradient, so a high temperature and a low temperature across, meaning these are thermal shorts, and we want to ask now what is the corresponding thing for thermal conductivity, right? That's really what we're after. So in a very similar analogy, if I were to ask how much heat current flows, and again, this is not electrical current, so we're going to say that this is going to be proportional to a certain thermal conductivity times the gradient in temperature, right? That's the analogy. Electrical current was electrical conductivity times the gradient in voltage, which is the field, right? Thermal conductivity is the coefficient that is telling you how much thermal current is flowing as a function of gradient of temperature, right? It's very standard, simple picture. And from here you can essentially figure out that the thermal conductivity will have watts per length, typically centimeter Kelvin units. You can kind of write that down. This will be the units of thermal conductivity, watts per centimeter Kelvin. And that's true for a three-dimensional object, three-dimensional semiconductor, amorphous material, whatever, right? So it's three-dimensional. That will be the units, watts per centimeter Kelvin. And just as so people have done obviously a lot of experiments of various materials with essentially trying to do this where you maintain maybe this side at 600 K and this side at room temperature, and you see how much of energy flow occurs across here, and by changing the temperatures and all, you can measure this now, just like you measure Ohm's law and electrical current, right? You measure this as well, right? Thermal conductivity. And there are many details of this. There are thermal conductivity at the junctions. There's thermal conductivity of this whole thermal resistance of this whole body, just like you have for electrical contact resistance, body thermal resistance, etc. Right? Okay, so that's the picture we're going to start with, and then just as a quick measure, what's a typical thermal conductivity of a material, for example? Any ideas? Meaning, let's say silicon or something like that. Would you have an idea? Yeah,
5.
That's a good number. Yeah, 5 is so 5 watts per meter Kelvin, watts per centimeter Kelvin. Yeah, right. So that's so it's there's some books prefer watts per meter Kelvin, some prefer watts per centimeter Kelvin, right? And so yeah, silicon actually would be closer to maybe 0.3, and that's and then as an example, okay, so that would be many semiconductors. Okay, so wait, watts per centimeter Kelvin, right? So it's about, if you want to convert to meters, then you just multiply by 100, so that will be 30, right? Or something like that. And many semiconductors, I would say that actually you're kind of right. Okay, so what's the higher end of thermal conductivity? Very high end. Materials like diamond. Diamond is very, very high thermal conductivity, and that in these units is 30 watts per centimeter Kelvin. Right? So I think what you said is I would consider that to be a little bit more correct. So a very low thermal conductivity will be of the order of, you can go very, very low. You can go 0.001. And remember, we're talking about solids. If you have vacuum, obviously, there's no concept of standard thermal conductivity. You can only radiate heat by black body radiation. We'll discuss those things today. Okay? So you can go as low as this. You have a comment? Or yeah? Maybe there's some doubt here. Yeah.
I was thinking if it should be Watts times Cn divided by.
Say that again?
Because the gradient of T is K over Cn, right? So the unit of K should be Watts times Cn over.
No.
Per unit area.
Per unit area, yeah. So the Kelvin is in the denominator. So I mean, if you want to think, so just like electrical resistivity will have, so instead of watts, you would actually have amps there. And amps is coulombs per second and things like that. And here it will be volts, so amps per volts. And then there will be a centimeter in the denominator because of the geometry. It's basically area divided by length. So they get a length here. Yeah, so this is correct. Actually, let me, I think I did have a few tables to show about the values of thermal conductivity. Let me just bring that up so that, okay, here's a quick example of thermal conductivity. So we have a very wide range, and what we want to do today is explain quite a bit of those numbers. So here's the experimental thermal conductivity. Diamond is on the top, it's 30. And if we look at silicon, gallium arsenide, there, actually you're correct. I think I was saying slightly off, 1.6 or 2-ish, 2. So you're more correct, about 5. So let's say about 2, many semiconductors. And you can go very low with some kinds of crystals and amorphous materials and polymeric sort of materials. I'll post a very nice article that reviews this, because this topic is not covered in Rocket, so I'm going to post that thing. You can read up. And the reason I decided to cover this topic today is because as devices have become smaller, more efficient, and are dealing with a lot more higher energies, thermal conductivity becomes increasingly important now than it was before, and it will become more so in the future. So essentially, we have the same transistors. We have transistors today that carry about the same current per unit width, but they are today 10 nanometer in dimension compared to 10 microns a few years ago. So they are generating the same amount of heat, but in much smaller volumes now. So getting the heat out is extremely important, and it's a very big challenge right now. So this problem has become increasingly important for even people doing semiconductor materials and devices that generally didn't have to deal with before, but now you have to deal with it. And also it offers quite a bit of opportunities because of the nature of the problem as well. Okay, so you have a range of these things, and what we want to do now is discuss in detail about what is thermal conductivity and track it down to a microscopic picture and look at what are the as with everything else, if we can understand experimental values, and this is calculation, so if we can understand it, we can identify why is it, how can you improve it, how can you reduce it if you need to, and so on. So that's really the goal. And what we'll start with is again, just like electrical conductivity, we will ask the question, what are the microscopic mechanisms for the flow of heat? Okay, that's really what the question here. And I think we have briefly discussed that problem in the very beginning. How does heat flow in a crystal? There are two ways, right? So heat is energy, and it can be carried from one end of a solid to another with two kinds of particles or quasi-particles, if you might. What are the two methods? There are many ways, but in a crystal, primarily there are two, right?
Phonons and electrons.
That's right. So you have phonons, which are lattice vibrations, and you have electrons that are obviously the charged particles. What about radiation? So, I mean, radiation obviously also can carry heat from one place to another, right? Which is photons, right? And it can, but inside a crystal, its contribution is minimal. inside a crystal. I mean, small dimensions. Compared to the other two, electron and phonons, they are much more potent in carrying heat from one end to another than radiation. And radiation, essentially, efficiency is relatively low, but things may change in the future because you actually are now, you can have a lot of heat carried, also heat carried out by light. If you have a LED, for example, right, it's possible to get a lot of heat out by using light, because that job is to carry energy out, right, using light. So there are other ways to think about it, and but we are going to focus on electrons and lattice vibrations or phonons. Now, electron. So I think you also know that. So essentially, we are going to say that the net thermal conductivity will be the thermal conductivity due to electrons plus thermal conductivity due to lattice. We're going to start with that. Obviously, there can be some interactions between them. Right? There can be cross terms as well. They can electrons can form bound states or quasi-particles with phonons, and then they could be called polarons. Or if you go to the extreme case in a superconductor, these get so closely coupled you form a Cooper pair. That's a new particle now. It's two electrons tied with a phonon and all that. We are going to not talk about those details. We're going to treat them separately right now. Okay, so I think it's very clear that again, I don't want to stress too much because we're going to focus on compound semiconductors. But which part of these two will dominate in compound semiconductors, or in any semiconductor for that matter? You have two contributions. Which one dominates in semiconductors? Any idea? Okay, let me ask the other question. Which one dominates in metals? Electrons. Right? So you have actually you have a certain lattice thermal conductivity and you have a certain electronic thermal conductivity. Electron density is extremely high, right? And so electrons dominate in metals, and in fact, if you calculate the electrical conductivity and divide it by the thermal conductivity for a metal, it's close to a constant. Does anybody know the name of that law? That's called a law. Electrical conductivity by thermal conductivity for metals is roughly a constant. And anybody know what that's called? It has a name. It's one of the famous laws which was discovered way before quantum mechanics, and then quantum mechanics explained it nicely. No? Okay, so that's called the Wiedemann-Franz law. Franz law. And so basically, and you have something called a Lorentz number and all that sort of thing. Okay. But constant, as in it doesn't depend on the metal, but it depends on temperature. So there's a temperature dependence. But and the reason for that is electrical current is carried by the same particles as thermal currents. They're electrons, and then you kind of I'm not trying to derive it. It's 3 or 4 line derivation in Ashcroft-Mermin or Kittel. You can go through, look at it. So, because I'm not going to discuss much about metals right now. Yeah. But I think we know very well that in a semiconductor, this is carried by electrons, obviously, electrical current, but this is not, right? So the Wiedemann-Franz doesn't quite work, right? Okay. So so what we'll do is discuss about semiconductors now, and I think we kind of know that because of the in some sense the lack of number of electrons, this term is very small for semiconductors, and this one is the dominant one. That is what dominates. So there's obviously another aspect to electrical and thermal conductivity. I think you know that so one can have I can sketch a picture like this. Here's my electrical conductivity, and here's my thermal conductivity, be it due to electrons or lattice or whichever, right? And what do we have, at this end of the spectrum? What are the classes of materials? High thermal conductivity, high electrical conductivity. So that would be metals, right? So typically that would be metals. And what about very low both electrical and thermal conductivity? Sorry? Yeah, but we have to be a little careful now. Insulators, that's right. Of course, we'll call it insulator, right? but what sort of insulators, right? And then that's why I have to be a little careful now. Here, yeah, I mean, you have amorphous materials typically, silicon dioxide as an example, or there are quite a few polymeric and such materials, but okay, so these will be let's call it amorphous insulators, but this is a general class. You can have some crystalline as well here. Some of them can be crystalline as well. What about this end? Low thermal conductivity but very high electrical conductivity. Any sort of materials that you know? Right. So this is a kind of an interesting. This and this are somewhat non-intuitive, and that's why we are going to focus on those. And both of them have to do with essentially compound semiconductors. Both of these, or semiconductors in some sense. So here, what you have is, if you think of a very narrow bandgap semiconductor, right? Or even a semi-metal for that matter. The gap is 0 or negative. But then they must have very heavy elements in them. The atoms are very heavy. At the bottom of the periodic table, like bismuth telluride and things like that. They are very high, so the gap is, they're almost semi-metallic, but the atoms are extremely heavy, and the electron density is not as high as a metal. So here you would have, these materials typically, okay, so let's, kind of roughly classify it. So heavy atom conductors or semiconductors, semi-metals or semiconductors. And semiconductors obviously would be a little bit this way. Semi-metals would be down. Would be, semiconductors with slightly lower electrical conductivity than the metals and all that, right? And what about this end, the top left? So very low electrical conductivity, very high thermal conductivity. This is even more, non-intuitive sometimes. Right? So, but what are the materials there? Examples.
Crystallinity with a high
band gap, right? An example being diamond is the best example. It sits on the top of the periodic of this table. Sorry, not the periodic table, but also in group 4 it is in the top of the periodic table. So these are, you can say very wide band gap crystalline, wide band gap crystalline insulators, but also light atoms and all that, right? So crystalline is important. Okay, so diamond, boron nitride, aluminum nitride, and that sort of thing here will come here. Right? So, and there are obviously a lot of uses of all 4 classes of materials. A lot of uses. For example, let's look at this one. What if you have a very high thermal electrical conductivity but very low thermal conductivity? What can you do with that? And what sort of devices do people make with that? Right, thermoelectrics. Essentially here you want to have heat as an input and you want to convert into electricity. So this is what you're looking for thermoelectrics, right? So, and you have, all these figures of merit like ZT, which would go as, some Seebeck coefficient, electrical conductivity by thermal conductivity, something like that. Right? So that would be a thermoelectric. And I think you can just even intuitively see why this will work well as a thermoelectric. Essentially the thermal conductivity is low, electrical conductivity is high. Therefore, if you have something sitting here at 600 K and here at room temperature, if you had a high thermal conductivity material, it would immediately try to equilibrate the two ends, right? That's the meaning. It's a thermal shot. Right. So, but it doesn't want a potential difference across it. But if thermal conductivity is low, it can hold a very large temperature gradient and convert that into a lot of electrical current across, right? And so you continue. It's a battery now, right? So that's a thermoelectric, and this property helps there, right? So, and so there, by the same token, this is really, this class of material is very bad for thermoelectrics. You don't want that at all because it wants to equilibrate everything right away, and so on. Okay. Okay, so I'm not going to further discuss these applications. We can read and imagine. I mean, there are quite a few, of course. If you have, but for example, also this end, you can see that for many applications, you may want a material that is very high thermal conductivity but extremely insulating electrically. Right? You don't want to electrically lose carriers or current into some regions, but you want the heat to be dissipated very well. Right? And this is extremely critical for many electronic and photonic devices. So we're going to kind of focus a bit more on how do you get high thermal conductivities. And there is a lot of rich physics and interest in these areas as well, but I'm going to focus a little bit more on that. I've already pointed out, bismuth telluride and heavier elements based semiconductor you can use for thermoelectrics, but I'm not going too much into detail. Maybe towards the end of the class today I'll say a couple of more things about this, but I'm going to focus a little bit more on this right now. And the reason for that is I think we see that for most devices these days, be it transistors, LEDs, lasers. So let's say you have a laser which is operating at 60% total efficiency, right? Let's say, right? That means 40% of this thing is going into heat. Right? Let's say you have a RF amplifier array in communications that is operating at 70% total, what you call as power added efficiency or total efficiency, but essentially a lot of it, even though it's a high efficiency, a lot of it is still going into heat, right? And that heat has to be dissipated and has to be carried out. And typically, for example, if you have a laser, we saw the laser structure, you have these quantum wells, and then you have cladding regions and all that, you have injection regions, right? So most of the heat is really being generated in the active region, right, where you get your spontaneous emission and stimulated emission. But the heat needs to be dissipated, so many times you will have to load it on some material that's reasonably close to this, but not too close so that you start tweaking and messing up with the device operation, and that is there to sink the heat. So there'll be a cooling, a lot of active cooling, passive cooling and such. So for those, you want this structure to be completely electrically insulated from the cooler, thing that's going to drive the heat out, but then you want it to be thermally shorted to it, so that you can. So that's where you go then, right? So and similarly for CMOS, digital switching, RF electronics, for lasers and high-end photonic devices. For both electronic and photonic systems, thermal engineering the device at the thermal level is become extremely important now. So we're going to kind of focus a little bit on that. But the stuff we're going to first talk about is very general, not necessarily limited to this high thermal conductivity, low electrical conductivity materials, but it's a general. We'll start with that and then focus on these properties. Okay, so let's start by, we are looking at this table, and there are some other parameters here, but let's not worry about them. We are looking at these numbers, and you can see now it's varying over such a wide range. Carbon, which is diamond, it's not graphite, by the way, it's diamond, it's not graphene. 30 watts per centimeter Kelvin. Silicon, 1-ish. And coming down, cadmium telluride, 2,6 material. This is 0.075. This is very low. So you're really spanning almost 2 orders, actually more than that, 3 or 4 orders almost, right, of thermal conductivities here. Indium arsenide, which is a very high high mobility semiconductor, 0.3 or so watts per centimeter Kelvin, right? So that's experimental, and then there's some calculated values as well. So let's start, and then there are parameters that go into this calculation, but let's start looking at how to understand thermal conductivity, right? and I hope we have, or rather, it's clear why I'm talking primarily about lattice right now. So it's primarily about lattice thermal conductivity for compound semiconductors. Okay. So, the lattice thermal conductivity is it's pretty clear. It's related to phonons, right? I mean, it's phonon vibrations, and the simplest model of phonons, which I can't remember, but I think we did discuss a little bit about this when we were talking about neutron spectroscopy and so on, right? So you have masses, right, and springs, and in a perfect crystal, all of them are sitting at their equilibrium positions, and the lattice constant is A. And then you let them. The idea is you come in and you move one of them, pluck a little bit, let it go, and then all of them start vibrating, right? And you have imparted it a certain energy, and then you can calculate how much does that, that energy that you have imparted, how much of a amplitude of vibration does it cause, right? So you can kind of find that out, right? And that sort of derivation, I'm not going to rederive it, but I think you can find out that omega as a function. So the phonon is going to propagate. Phonon is going to propagate as a wave. Wave length is lambda, and 2 pi by lambda is what we are going to call as the wave vector, like we always have in this course. So 2 pi by the wavelength is the wave vector. And you have seen how you derive the phonon dispersion, I hope, right? I mean, essentially you pluck one and then look for the normal modes and write down here's a possible, each spring will follow a force is equal to minus kx sort of Hooke's law behavior, right? And then from here you can straight away get in a couple of lines that the frequency dispersion, it's a wave, and wave has a certain frequency and a certain wavelength, and it will look like I think it's like square root of k over m, where m is the mass of the atoms, times sine q a over 2. That's what you're going to end up with. This is the single atom lattice. Sorry, I'm going to. All right, don't worry, I don't have that access, but this is the dispersion, right? Frequency, we'll come to those things later, but frequency as a function of q is going to look something like that. Any questions here? I've not derived it, but hopefully you're familiar with this, right? Or any doubts? Right. Okay. So the frequency goes as a sinusoid as a function of the q, or the wavelength, and these are just the spring constants of the masses and all that. And the spring constants and the masses are exactly the same that we discussed during when we are discussing about coherent growth and alloy and this Keating model. Remember, we were strain, effect of strain on formation of dislocations is the same thing. This k is the same as the ones that we had seen before there. C11, C12s and all that. It's the same thing really here. Okay, so the frequency of a phonon or a wave that can be launched in a semiconductor, either because you intentionally strain it and let it go, or because of heat energy itself, instead of you doing it, heat itself, right? This is going to cause that sort of a vibration. And if you sketch this now, sketch this frequency, right, as a function of q. So it's a sinusoid, right, and it's going to have a certain periodicity, and here from this picture, sorry, I think I sign, it should be absolute value on that, absolute value, it's no negative, so so when you sketch it, it's going to look like this, right? And it's gonna, so it starts out from 0 and then goes something like that, and that's how omega versus q. Okay. Just as a order or measure of what is the maximum frequencies here, if I, instead of writing omega, I can always write h bar times omega. That's the energy scale, right? And this here would be of the order of tens of milli-electron volts, MeVs, tens of milli-electron volts. 40, 30, 10 for some semiconductors. And we'll see the heavier the semiconductor atoms, the lower this is. The lighter the semiconductor atoms, the higher this is. Right? So why? Because M is sitting here, right? M is sitting here, heavier is the mass, the lower is this whole curve, right? So the magnitude is smaller, phonon frequency is smaller. Yeah. Okay, so The other thing is for very small q, or q a over 2, going to 0, or very small q, or let's put it much less than 1, or in other words, q is much less than 1 over a or 2 over a. So 2 pi by wavelength is much less than the, or well, wavelength is much larger than the lattice constant. That's when q goes to 0. Right? Very small wave vector, or in other words, very long wavelength of the phonon. Right? For those values, we're looking obviously at in this window, right? And in that window, I think we know that sine x for small x is roughly equal to x, right? So what you get from here is omega of q becomes roughly equal. You can plug in all those things, k over m, and sine becomes just qa over 2, and you can just cancel out all these other things, right? So you get that omega at small q's is just square root ka squared over m times q, right? Omega, frequency of the phonons is proportional to the wave vector, right? Frequency is proportional, and then there's a certain constant in the front, right? Okay. So this part, what he's saying is, well, this part is linear, and that you can already see when you sketch it. It's linear, and the slope of that, what is this quantity then? So frequency is wave vector times some quantity. This quantity is a velocity, right? Frequency, wave vector, so 1 over length, 1 over second. So length over second is velocity. And what is that velocity? Physically, what is that velocity? Yeah, it's the sound velocity in the material, acoustic, right? Sound velocity, and that's the v speed of sound in the material. And typically of the order of 10 to the power 5 to 10 to the power 6 centimeters per second. That's how fast sound moves in most semiconductors. In air, it's what, 330 meters per second or something like that. In semiconductors, it's much faster. And that's how much it is. So air is very rarefied atoms, but semiconductor is a much more dense set of crystals, so that sound can move faster. It can be a little higher too, but yeah. Let's put it roughly 10 to the power 6 or something like that. I think some of them are lighter, slower too. So sound velocity is of that order, and I think I think 2 or 3 classes, or maybe a little bit more. Some classes ago, I'd mentioned that this is somewhat inevitable, that you will have, this is a zero energy excitation of the lattice. It's related to this, what's called this Goldstone modes, because of formation of a crystal breaks the symmetry of, is a linear symmetry of an atom. So this is an example of a Goldstone mode, and essentially, even before you did all this calculation, you could have said that there must be something like this. That's all, and then you do the calculation and figure out that yes, of course there is. Okay, so now that's the simple picture, and then so is that clear? I mean, and then from here you can also, for example, the mass of the atoms, the lattice constants from spectroscopic X-ray sort of measurements, and if you measure sound velocity, you can effectively get what is k. Right? So there are many other things you can kind of use it for example, right, and all that, yeah. And you can also calculate k from atomistic pictures and springs and all that, right? Okay, so that's about acoustic phonons, and then we know that if instead of a single atom, let's say I had, this was attached to another atom, and then here your bases were slightly different, or some, or this was atom A, this was atom B, and so on. So that would be a compound semiconductor. The 2 atoms, or even silicon has 2 atoms in a unit cell, right? 2. And when you add the second one, you have just like, if you remember, we're looking at electronic band structure. Every time you add an orbital, you get another band, right? In the same way, every time you add another atom in the unit cell, you get another band here, and that band here would be called optical, right? And so the optical phonon mode is when you have n, which is the number of atoms in the basis, is greater than equal to 1. You will have that. Let's call it big N. That's I think what's used in those notes. Okay, so yeah. So that's optical phonon. What is physical meaning of optical phonons? I think so if this is A and this is B, in an acoustic phonon, they are always vibrating in the same phase, meaning if this has moved to the right, this has also moved to the right, maybe a little bit less, and the one is a little bit less. So they're in phase. If it's moving to the right, that's to the right as well, right? And that leads to this mode. Whereas if this is moving to the right and this is moving to the left, they are out of phase. And then again, A is also moving to the right, maybe a little less, B little less to the left, and all that, right? So there are kind of two sublattices. They're vibrating out of phase. That's what leads to the optical phonon mode. Costs a lot more energy to get there, and it doesn't go through zero. It doesn't have a zero energy. It doesn't go to zero. And I think you can just think a little bit about it, why this must be so. Okay, so the important points here are that the optical phonon branch has very small dispersion. What does that mean? It means its bandwidth is very small. Delta of energy, or delta omega, is very small, whereas the acoustic phonon has a much larger bandwidth. Very large bandwidth. Acoustic phonon at 0 Q or very long wavelength is linear, and it's related to sound velocity. But obviously it starts rolling over. It doesn't go linear all the way. It starts rolling over and stops. And the net bandwidth from one semiconductor to another depends on the mass, and that's the very important thing. 1 over mass determines, how 1 over mass tells you how large you are and all that, right? So those are the three important things about the relation to the microscopic atomic properties. Okay, so now the thermal conductivity, that's what we are after, right? Let me outline a typical picture of what happens in a semiconductor device under operation. So for example, if you're taking, if you have a LED or a laser or a transistor, you have an electronic band structure, right? This is a phonon band structure, EK, or dispersion of phonons. You have an electronic band structure, and if I were to plot the electronic band structure versus small k, k is that of electrons, 2 pi by wavelength of electrons, 2 pi by wavelength of phonons now, right? So I think you know that for electronic band structure, we are talking about electron volts in the scale, right? Here, this is millielectron volts, tens of millielectrons, so how about 100, right? And I think you have done, for example, also in your very first assignment, you did all these band structure, sort of calculations. I'm just going to sketch a few. So you have valence bands, and you have, conduction band, right? So let me sketch it. So conduction band and all that, right? And but this scale is much larger than this. What I'm trying to say for first things. Right? And then what will happen is typically in a semiconductor device, let's for example look at a transistor. In a transistor, you apply a very high you apply a voltage, and the electrons start accelerating, and they climb up in the electron band structure, right? So the gain energy, and as they gain energy, they start from very long wavelength. K is 0 means very long wavelength, and as it accelerates up, as it goes up in energy, it gets, the wavelength gets compressed, and all that. It gets shorter and shorter, right? Because it's 2 pi by that, right? So it gets shorter, but then it will at some point, as it climbs here, it's going to reach a certain energy. I mean, this is exaggerated. It's going to reach a certain energy when now, actually at all points, even when it goes here, you can see right away the electron is still in the lattice, so it can start dumping some of its energy into these modes. Starting from 0, it can start dumping its energy into here. It can create an acoustic phonon. That's the way to look at it in a band structure picture. Physically, what's going on is an electron is moving along and is going to collide with the atom and set off those vibrations. And that's really physically what's going on, right? And in band structure picture, that's what's going to happen. That essentially the electron tries to climb up, but then it emits a certain quanta and excites a certain mode here. All right, excites a certain mode here, and electron loses that energy and momentum, and that's picked up by the phonons. Right? So energy and momentum are always conserved. Right? The total energy and the total momentum are always conserved. The question is, where is it? Right? Is it there or is it here? So they'll interact and exchange these particles or exchange the energies. So from the what I want to do, I mean, and you can kind of precisely calculate all these numbers. If an electron starts accelerating, how fast, or what's the rate at which these phonon modes start getting populated, or what's the rate at which these phonon modes start getting populated. You can calculate this for many semiconductors from from the golden rule, and we cover that in the transport course typically, right? The details of those, what are the rates and all that. But let me just say the end results of that. So for example, you can see right away that unless the phonon, the electron energy is larger than the optical phonon energy, let's assume this is very flat. Let's call it h bar omega optical. If the electron energy is not larger than the optical phonon energy, it cannot emit an optical phonon. It cannot excite it, right? Because you need a certain threshold to emit the optical phonon, right? But when it does, the rate of optical phonon emission in compound semiconductors is way higher than the rate for emission into acoustic modes. Does it make sense? I mean, once the electron has sufficient energy of above a few tens of MeVs, and it can excite optical phonon, the rate of exciting optical phonons is much higher than the rate of exciting acoustic phonons. So essentially what happens is, the picture to take in is, you have a certain electron distribution, electron gas, 2D electron gas, or whichever, and then what you're doing is we have applied voltage and you're pumping in energy into the electron system, and the electrons start drifting and accelerating, right? And that happens effectively instantaneously. The moment you start apply the voltage, electrons respond. I mean, there's limitations of speed of light and all that, but those are not measurable at this length scales. But then it actually goes way out of, basically there are certain time scales for emission of acoustic phonons and certain time scales for the emission of optical phonons. So in typical compound semiconductors, the optical phonon emission rate would be of the order, meaning I'm kind of qualitatively drawing this picture. So of the order of picoseconds is how long an electron can exceed this energy, meaning if t is equal to 0, you turn the start the electric field and electrons start accelerating, and it stays here at a high energy state. It's feasible for it to emit an optical phonon, but it needs at least a picosecond to do that. That's the time scale, and this comes from golden rule sort of evaluation. So I'm not deriving it. So about a picosecond. Right? So if your transit time of an electron from one end to another is sub picosecond, the electron wouldn't get a chance to emit an optical phonon. It will be through before it can even excite the optical phonon mode. So that would be typically called velocity overshoot and ballistic and all that. So there's no chance for exciting the optical phonon. But in a long device, you will end up dissipating that much energy. So it will go in. So that's the order of time. So the idea is the energy flow in these devices typically would be the energy from the battery, which is driving your transistor or your laser, is first going to go here, then it's going to come to the optical phonon modes. So that's what is going to, where the energy is dumped, the optical phonons. But the problem with optical phonons is, you see, they have no velocity. The velocity of any group velocity, I think we've talked about that, is basically d omega over dq. Right? That's group velocity. The slope of the dispersion is the velocity. Right? And for all practical purposes, the optical phonon you can consider to be flat. It's actually very little curvature, very little dispersion, and their group velocity is 0. They don't really move anywhere. Right? So the lattice will vibrate, but it's localized. It's not going to dissipate the heat at all. It's going to just stay there, right, till something happens. I mean, it essentially, and what is that clear? I mean, this is not going to carry the heat away for you at all, because it's not going anywhere. Right? You want to carry your heat away from the device, but it's going to just stay wherever it was generated. The energy stays there in the vibration. Is that clear? All right. So clearly, what one needs then is this acoustic, the optical modes to go into the acoustic modes, because the acoustic modes are moving with speed of sound, and they can carry the heat out. Right? So therefore, what happens is So you dump your energy into these optical modes first. The electrons dump their energy there, and then there is now a time scale in which what happens is, for example, this is the optical mode, and then it has to decay into 2 acoustic modes, for example. It's to decay. One phonon mode has to decay into multiple acoustic modes such that the energy is conserved and momentum is conserved, because they're always conserved. Right? So, for example, if you started at a 0Q mode here, very close to 0Q mode, you must go to exactly symmetric plus Q and minus Q, and you must be, if this is h bar omega, this must be half h bar omega, that must be half h bar omega if there are 2 phonons, if one goes into 2. Right? Does that make sense? Yeah. And this particular decay channel for phonons is called the Clemens decay channel, Clemens decay of phonons, and after the person who actually realized that this is what must be the case. The order, again, the time scale for typical semiconductor would be a few picoseconds. Sometimes about a picosecond, but a couple of picoseconds is how long it takes after you excite optical phonon mode for it to go into decay into acoustic modes. So from optical modes, you're going to go few picoseconds. You're going into acoustic modes, right, of phonons. That's where the energy goes. And then the acoustic mode's job is basically they're going to carry the heat away, because the place where you generated it inside your laser bar, let's say, is very hot, and out here is very cold or much colder than that, so the heat current starts flowing. And the acoustic modes are carrying the heat current. The sound waves are what is really carrying it out. Okay. Does that make sense? I mean, that's the microscopic picture of all the details. And acoustic modes, I think you can estimate roughly sound velocity is 10 to the 5, 10 to the 6 centimeters per second, as you mentioned. And if your devices are, if your heat sink is out here and your device is 100 microns, you can see what sort of time it will need to calculate in the sound velocity divided by that, right? And that typical thermal time scales would be of the orders of microseconds to milliseconds. So that's how much it will need from the heat sink, essentially for the energy to get out there. So and the battery connects here at immeasurable time scales, and essentially this is the whole picture now. There you can see that the electrons are trying to lose their energy to optical phonons at picosecond rates. Optical phonons are trying to decay into acoustic modes at few picoseconds rates. Acoustic is carrying the heat out, and here's your sink for wherever temperature. If you have a water cooling, if you have a fan, wherever, right, the energy goes out from there, right? So it started from the battery and ended there. And if any of these time scales is, for example, much faster or much smaller, you'll have quite a bit of buildup of something, non-equilibrium values and all that. For example, electron temperature effectively will be always much larger than the lattice temperature. Lattice temperature is controlled by this, electron temperature by that. So the energy flow is this way. So for the electron, so that we call a hot electron, right? Sometimes what happens is in gallium nitride and some of this aluminum nitride, this electron to optical phonon can be of tens of femtoseconds. It's much faster. The optical phonon coupling is very strong in a highly polar material. In that case, this is a few femtoseconds, but this is still a few picoseconds. So what happens is the energy, a lot of energy here, but a lot of energy is also stored in the optical modes. And that's sometimes called as a hot phonon, which is an interesting name because phonon is heat itself, but it's a non-equilibrium phonon, so way out of equilibrium. Because if you do a measurement of the optical phonon distribution, its effective temperature that fits the Bose-Einstein distribution, for example, is way higher than the lattice temperature, physical lattice temperature. The lattice temperature is related to acoustic phonons and the vibration. So, okay, so that's a detailed picture of what happens in the microscopic range. But essentially, the thermal conductivity is business that happens in this window. It's not in the upper window. So after all the energy has entered the acoustic modes, that's where the thermal conductivity comes in. And thermal conductivity is dominated by acoustic phonons, and optical phonons have a small role to play. And I will explain what I mean by that. Okay? Is that clear? I mean, I just glossed over, but at least it's important to know the time scales. I think it's and where can there be bottlenecks, and so on. Yep. Yeah.
So if the battery doesn't give enough energy to the electron, it will skip the optical phonon.
Say that again? Yeah.
Oh, if the battery doesn't give enough of energy to the electron,
Yes.
we will skip the optical.
Yes, good point. So for example, let's look at a concrete example. You get say aluminum nitride, and this is about 100 millielectron volts is the optical phonon energy for aluminum nitride. And let's say you have a battery and you are applying only 0.05 volts, because 100 millielectron volt is 0.1 volt, right? You're only applying 50 millivolts. I mean, then the electrons really have, even the highest energy electrons don't have enough energy to excite this, right? So in that case, you will not excite this at all. You will only excite these modes, right? And so this is more of a very high energy, high field phenomena when you saturate and all that. At low fields, this is electrons essentially emit into these modes and things. That's how you reach equilibrium.
How fast would that? Because now
Oh yeah, so this can be tens of femtoseconds, but of the order of picoseconds, and this scattering rate is also slightly longer, meaning it takes slightly longer, but it's also of the order of picoseconds. I mean, it's not milliseconds or microseconds, of the order of picoseconds. The thing is, though, every emission into this mode carries away a lot of energy. Every emission into this mode carries away very little energy. So therefore, even though the time scales are similar, these modes are much more potent in carrying the energy out, because they're, everyone is here. You have 1,000 of those will combine to give you only one of those. That's the thing. So its time scales is not as important as the number. The energy dissipation is much more. Yeah.
Opticals don't carry the energy away. They just
From the electrons. No, that's right. So they will definitely carry the energy, take the energy away from electrons, but they will not dissipate it here by themselves. They have to go to acoustic mode. That's a good point, right? Which is why if you are emitting very fast, but you are decaying very slowly, you get a very huge buildup of optical, the hot phonons and all that, and you have to figure out how to deal with it. It's actually a weird situation, and we'll see. So for example, the maximum of this acoustic mode frequency, the maximum is, let me just write down a couple of rough estimates. So the maximum value of the acoustic mode, if you have, instead of one mass, if you have two masses, M1 and M2, when you have optical and acoustic modes. So omega will go as square root of k over M1 plus M2. Basically, the maximum point here is if your atoms, the two masses are very different, M1 and M2 are very different, let's say. A good example is, actually a very good example is gallium nitride. Gallium is heavy, but nitrogen is very light. So what happens is the difference of this is what you can call as the phonon band gap. That's what it is, the gap in the phonon spectrum. The difference is related to 1 over M1 minus 1 over M2, or the difference in the masses of the two. That's what it's related to. Just like your band gap in an electronic semiconductor was related to difference in potentials of sitting at point A or point B or things like that, right? Electronic potential. Here it's related to that. And if the mass difference is very large, then it may so happen that the phonon energy here, let me sketch this a little, I think it's become a little messy, so let me clear it up. In gallium nitride, as an example, what happens is the optical phonon energy is about 92 millielectron volts, 92 MeV. But the maximum of the acoustic modes is close to 40 MeV. That's the max, right? So you see, you don't have the Clemens channel here at all. You can't decay 92 by 2 is 46. You can't go to acoustic modes. It's blocked. Right? Does that make sense? You can't go into 2 because if you want to go into 2, you need 46 and 46 MeVs, but don't have it because you ran out of modes. Right? So this is so here what happens is there are so that was the longitudinal optical mode to which electrons actually couple. There are a couple of other modes which I probably should have said. So there's transverse optical modes here, which electrons don't couple to directly, but then they have to go through an even more inefficient process first. And then the transverse, cascades down, and then you can finally get in there. So that process slows down the decay. There are examples like that. So, but what I'm saying is the energy from the electrons can be dumped very easily into the allophonon modes. And whether the LO goes from here to there, that's the harder part. That's where the, in some semiconductors it's very easy. If you have heavy, or the masses are very similar, M1 and M2, then it's very close, and you get quite a bit of possibilities. You can get a lot of possibilities for decay. Whereas for some you have none. Those are slow, and that's one of the pictures to look at. Okay, so those numbers have been looked at in reasonable detail, but a lot of those things are still being, I would say, hotly debated and figured out and all that. Okay, so what I want to get to is, so if you have a 3D crystal instead of a 1D model that we talked about, I think we know that you can have a longitudinal mode, longitudinal acoustic, where the atoms are, so the wave is going in this way, your Q vector wave is propagating in this way, and the atoms are also vibrating in the same direction, right? So this goes, there's a wave this way, and the atoms are also vibrating. That's longitudinal. But if you have 3D crystal, you also have chances that the atoms vibrate in the perpendicular modes. That's your Q, but then you have two transverse modes, right? One longitudinal and two transverse. So as a result, you will have two more modes here, transverse acoustic modes, and in general you will have three acoustic phonon modes, one longitudinal and two acoustic. And optical modes will be, let me write that down. Optical modes, there will be 3 times n minus 1, where n is the number of atoms in the basis. If you have only one atom in the basis, there is no optical mode, right? And if you have 2, then there are 3. If you have 3 atoms in the basis, or 4 atoms, it starts increasing. Right? And it's very similar to how many orbitals you choose and how many bands you end up with. It's the same thing, really. So you must end up with 3n if you have n atoms, and each has 3 degrees of motion freedom, right? You must have total of 3n modes here, 3n bands here, and that's what the reason for it. Okay? Now, the thermal conductivity, the acoustic modes really play no direct role. It has an indirect role. It's primarily by the optical phonons play very little role. Indirect role is primarily dominated by acoustics. Right? And so if you start looking at quantitatively how do we write down the thermal conductivity, so that's something we can discuss a little bit right now. The thermal conductivity is very closely related to, for example, the maximum point here, which is the maximum acoustic phonon energy. We can write that as h bar times omega, right? And that frequency at which the frequency that characterizes it would be called the Debye frequency, the Debye after Peter Debye. This is just the scale is related to Debye frequency, and you can from there you can equate it to a certain temperature, theta, right? And that would be called the acoustic Debye temperature for acoustic modes, A, theta A. I'm just following the same notation as the book. So essentially the Debye temperature is the maximum frequency of acoustic phonons over Boltzmann constant. This is your Debye temperature. Does that make sense? Okay. And right away you can see that if you have light masses, you will have higher Debye temperature. Right? Light masses would lead to a slightly higher value here, and then get larger Debye temperature. So that's the first thing that appears, right? The other thing is if you are looking at linear dispersion, right? Linear dispersion, omega for very small q looks like sound velocity times q, right? And if you remember, this is actually a problem that you guys solved in one of your earlier assignments. Where was that? Maybe assignment 2. Yeah, okay. So I had asked you to, so just every band here, you have a density of states for the phonons. Right? If you have a linear dispersion, Ek is equal to something like that. You have a density of states, and you don't care actually what particles these are. It just so happens here there are phonons. So if you have linear dispersion around here, and you ask how many phonon modes are there as a function of my omega or energy, what is my density of states of phonons? Right? And you have linear dispersion. Linear dispersion in 3 dimensions. Very important. It's important what dimensions you have. For 3 dimensions, the density of states goes as square of the omega. It increases as square of omega. You had calculated that, and it's just a mode counting picture. Essentially what it's saying is, if I were to plot the density of states of the phonons in 3D, it's increasing as omega squared parabolically. Right? Is that clear? So now what you can do is come back to the thermal conductivity picture and say that, well, what if I had, you know, so the Debye temperature is clearly defined for, you know, a band like this, but then you can have multiple, you know, longitudinal and transverse and other modes as well, right? And you can say, what can I get an effective Debye temperature by including, you know, all the details of the bands, and what you can do is do an sort of averaging over many of the. So there's a DOS for LA, there's a DOS for TA, and all these other modes, right? And you can do some sort of an averaging, which is kind of shown there. You're averaging your Debye temperature within essentially the density of states over many modes. It's not. I'm not trying to kind of say this is extremely important right now, but you just have to keep in mind that there can be many modes, and the Debye temperature is related to each mode and things like that. So you get an effective Debye temperature in the end, and that's you know, if you convert it, for example, you know, if you're you can see from here it will be of the order of few hundred kelvins. You know. If it's 30 MeV, it will be close to 300 Kelvin. If it is you know, 100 MeV, it will be close to 800 or 900 Kelvin and all that something. That's roughly the order of magnitude of the Debye temperature. Now, a very important property of crystals is if your crystal was completely perfect. And this is a very intriguing property you may or may not have thought about, but if a crystal is perfect, you know, it's a perfect crystal, and all the interactions between atoms, if I vibrate, if my total energy, if I, you know, have a displacement of x, goes as, you know, whatever is the internal energy plus half kx squared, you know, that's the picture of a harmonic oscillator, right? If this was my total energy of interaction between, you know, of vibrations of atoms, and another way to, or you can write it in terms of r, okay, r square. I think we know that the origin of that is because as the atoms are distance r apart, we're looking at this minima here, and that's the oscillation, right? And you move it a little bit this way, that way, it's a parabola here, right? But the interesting thing is, if it's a perfect parabola, if your total energy is given by this, that crystal actually can never dissipate the heat. It can never dissipate heat. Just in the same way that if your semiconductor, you know, electrons moving through a semiconductor, if the semiconductor is perfect, there are no defects and no phonons and all that, it cannot lose its energy. You know, you need defects to get resistivity and scattering, right, and all that. Does that make sense? You know, if a perfect crystal, electrons move through ballistically, there is no resistance inside the crystal. It's all outside in the contacts and all that. In the same way, if your vibrations are completely modeled by just a kx square or a parabolic term in the energy, this thing will have you know, infinite thermal conductivity. It cannot have a finite thermal conductivity. Just like, you know, the analogy being, if you don't have defects, you have infinite electrical conductivity too. There's no scattering. Right? So, but in reality, we know that this is not a perfect parabola. Right? There are what you call as anharmonic terms. Anharmonic terms. So in a 1D model, you will get some constant times x cubed plus quartic terms and all that sort of thing. So you will get those. And so that is really, this term is what is responsible for thermal conductivity. This cannot give you thermal conductivity. Okay, so what does that physically mean? Meaning, if I heat up the crystal, they will coherently vibrate, right? And the energy will never get out from the crystal. If I connect with something, it's not going to get out. It's going to stay within the crystal coherently. The energy will be trapped in the vibrations. That's really what it means. It's not going to be dissipated out. Whereas if you actually have the anharmonic terms, the third and the fourth order terms, you actually can now talk to and get the heat. They will not be stuck in this mode. You can get it out now. So it's very similar to a Q factor of a cavity or something like that. If your Q factor is infinite, the light can never get out. I mean, you can't build a laser if it's infinite. You have to have a little leak somewhere, and then the energy goes out there. Right? So it's very similar. So if you don't have those terms, it's the crystal is an infinite Q cavity for heat. That's what it really is. So it contains the heat waves completely coherently. But because this is, if you really look at this carefully, it's some sort of a Leonard-Jones potential and all that. So there are anharmonic terms around here, and that's what leads to, So for example, these quadratic terms would be what are called one phonon process. Essentially, these are terms where phonon and phonons collide with each other now. So this is a 3-phonon process, it's a 4-phonon process, and so on. But that's what really leads to the thermal conductivity. Right? And so one can approach it from a condensed matter microscopic picture, or one can approach it from a more thermodynamic picture as to how to model thermal conductivity. And one of the nice ways to look at this problem is the thermodynamic approach, and I'm going to just outline what that is. I think we're running against time now. So if your crystal was perfectly, if this wasn't there, I mean it's a perfectly harmonic crystal, then it turns out that actually if you apply a certain amount of pressure across it, hydrostatic, uniaxial, whichever, then the volume change due to pressure will be 0. You can actually prove it. Right? If you have a perfect crystal, it's non-zero. Right? If there's no anharmonic term, you cannot change the volume of the crystal. If you squeeze it this way, it will stretch out that way and all that. Right? You cannot change it. But in reality, there is a certain volume change because of the existence of this thing. Right? So what you have then is you apply a pressure and you have a slight volume change. And that is a measure of this term. Right? And you take that energy divided by the amount of energy you put in. This has units of joules, PdV, right? And this quantity is called as the Grunisen parameter. Now, the Grunisen parameter does it make sense? So it's a measure of the anharmonicity of the crystal. It's a deviation from the perfect harmonic crystal. You can actually write down energies as h bar omega and these as lattice constants and all that. So what you can actually show that this is equivalent to delta of omegas. What is this omegas? So this is the thermodynamic macroscopic picture. These are the omegas of the phonons. It's the change in the phonon frequencies over omega times delta V over the volume, or change in the lattice constant but cubed, change in the volume. So this is how the Grunisen parameter looks, and typically it's written as a so you see it's dimensionless the way it's written, energy over energy, and typically it's written as natural log of omega I over d natural log of V. D natural log is give you d by that, right? That's how it's written. It's a Grunisen parameter, and it's a measure of this anharmonicity, and it plays an absolutely critical role in thermal conductivity. And let me just say, so you can take this microscopic picture, calculate it, you can do a physical measurement, calculate it or measure it, and you will end up with something like roughly 1.0 to 2.0. That's the range of the Grunisen parameters, of the order that much. And sorry. So here are the Grunisen parameters of many semiconductors. Diamond, silicon. It's slightly less than 1 for these, and 1 and all that. Close to 1, and some it can be higher. Right? Okay, so I think what you can intuitively see that if the Grunisen parameter, first of all, is it clear physically what it means? I didn't derive all the details, but this is the definition of Grunisen parameter. It's the change in volume by application of pressure, and it's somewhat, I don't know, it could be very easy to imagine, but if you had perfect crystal with perfect no anharmonic interactions, you will not be able to change the volume by applying pressure and all that. But if you can, then that measure, is called Grunison parameter. So thermal conductivity is, so I think you can qualitatively see that if my crystal is more perfect, I will have a more higher thermal conductivity. Because the most perfect crystal is when you don't have anharmonic terms, lattice waves can keep going. There is nothing to scatter, right? And my thermal conductivity is infinite. That means if I have a small Grunison parameter, I can, it's closer to the ideal. So I'll have a higher thermal conductivity, right? So the atoms, the crystals that are much stiffer and all that will have a higher thermal conductivity. So the net thermal conductivity, I'm kind of out of time. Let me just write down, we talked about most of the parameters here. And now, the net thermal conductivity now, I wanted to go from this picture to that, but we can maybe finish that in the next class. So is a combination of all these things. But let me just go to the end result. Once you evaluate through, what you get is the thermal conductivity will be equal to a certain constant in the front, and then what you'll have is masses of the atoms. We talked about that. Yeah. And then what you'll have here is the Debye temperature cube, third power. Right? And there's a volume of the unit cell over the Grunison parameter squared, a temperature, and then what you get here is the number of atoms in the unit cell, or the basis, to the power 2/3. Right? That's what you end up getting after all is said and done. This is the thermal conductivity near room temperature, and basically this is what you call as the high temperature, higher room temperature thermal conductivity, roughly. That's how it's going to look in the very end. And you see, one of the most important parameters sitting here is the Grunison parameter in the denominator, and obviously if it is, if Grunison parameter is very low, the thermal conductivity is very high. It's more harmonic. But the other two parameters you see are, you need a high Debye temperature for a high thermal conductivity, right? And you need light atom masses and all that, but that's not, that's one of the parameters. But then also you need very simple crystals where the coordination number, or the number of atoms in the bases, is not very high. So for high thermal conductivity, the three requirements are high Debye temperature, small Grunison parameter, and small number of atoms in the basis. And then you see diamond and all really satisfy this in a beautiful way, which is why you get a very high thermal conductivity. So the point here is light atoms are not enough. You need more. You look at gallium oxide or aluminum oxide, sapphire, their atoms are very light, aluminum and oxygen, but the thermal conductivity is abysmal. And the reason for that is Grunison parameter is not right, meaning it's high and not too many atoms, 5 atoms, Al2O3 or Ga2O3 and things like that. So we'll just finish up this discussion in the next class, compare some of the experiments to theory, and then spend the rest of the classes discussing about epitaxy and all that. Okay? So just as so I'm extending the due date for this assignment to Monday, those who came in a little late. All right, thanks.